Welcome to the Power Electronics class. Myself B. Veernarayana, Senior Assistant Professor, Department of Electrical and Electronics Engineering. We are in second unit, AC to DC converters, and up to now we completed the single phase half wave control converters with R load, RL load freewheeling diode, with and without freewheeling diode, RLE loads. Later we discuss the single phase full wave converters, both midpoint type configuration and bridge type configuration, and we discuss single phase fully controlled converters and single phase half control converters. And coming to the three phase AC to DC converters, here we are completed the three phase half wave controlled converter with R, RL, and three phase fully controlled converter with R, RL and RLE load. And in the last class we completed the three phase semi converter with R load. Now we are in three phase semi converter or half control converter. This is the circuit diagram representation. Here we have three controllable devices in the positive group or upper group, and in the lower group or negative group three uncontrollable devices are there. Those are numbered as D1, D2 and D3, D1, D2 and D3. Here we go with the RL load. And if you go with the three phase semi converter or half control converter with the R load, this is the circuit diagram. If you go with R and RL loads, if alpha less than 60 degrees, that half control converter behaves like R load. So if we go through this R load, these are the output voltage waveforms for alpha equal to 0, alpha equal to 30 and alpha equal to 60. If you choose alpha equal to 90 degrees, then we are getting, if alpha greater than 60 degrees, we are getting the discontinuous conduction mode. And the output voltage equation, here we have two cases. Depends upon the firing angle, the converter is able to operate either in continuous conduction mode or discontinuous conduction mode. If you go through the first case, and if alpha less than 60 degrees, then we are getting the continuous conduction mode. If we go through the continuous conduction mode, the output voltage expression is given by 3 by 2 pi integral 60 plus alpha to 120 VML sin omega t d omega t plus integral 60 to 120 plus alpha VML sin omega t d omega t. By simplifying this expression, take VML common, 3 VML by 2 pi integral sin omega t is minus cos omega t between the limit 60 plus alpha to 120 plus integral sin omega t is minus cos omega t between the limit 60 to 120 plus alpha. By simplifying this expression, 3 VML by 2 pi minus cos 120 minus of minus plus cos 60 plus alpha minus cos 120 plus alpha plus cos 60. So by simplifying this, here cos 120 value is given by 1 by 2 plus cos 60 plus alpha minus cos 120 plus alpha is written as cos 180 minus 60 minus alpha, cos 60 is 1 by 2. By simplifying this, finally you are getting the output voltage expression as 3 VML by 2 pi into 1 plus cos alpha. And if we go through the discontinuous conduction mode, in second case for alpha greater than 60 degrees, only we are getting the three pulses. So 3 VML by 2 pi integral alpha 2 pi VML sin omega t d omega t. By simplifying this expression, we are getting 3 VML by 2 pi into 1 plus cos alpha. And now we go through the three phase semi converter or half control converter with RL load. Here what I said, even though if we consider the inductive element in the load, if alpha less than 60 degrees, then there is no effect of inductor. Simply this converter is operates under R load. And if you go with alpha greater than 60 degrees, then we are able to observe the effect of inductor. So you know, depends upon the value of inductor, the converter is able to operate either in continuous conduction mode or discontinuous conduction mode. If you have the large value of the inductor in the load, then the converter is able to operate in continuous conduction mode. If you have the low value of the inductor, then the converter is operates in discontinuous conduction mode. First we go with the continuous conduction mode, and for alpha is equal to 90 degrees, I just want to draw the output voltage waveform under continuous conduction mode. So if you want to draw alpha equal to 90 degrees, then first you go through the timing diagram. If I am taking alpha is equal to 90 degrees, where the T1 comes to on state, plus 60, that means 90 plus 60, 150. From 150 onwards, T1 comes to the on state. So from 150 to the conduction period of each device is 120 degrees. So 150 to 270, T1, 270 to 390, T2, after that T3. Before T1, you have T3, ending portion is 150. Then what is the starting period? 150 minus 120, 30, 30 to 150, T3, and 0 to 30, T2. Those are the conducting period of positive group devices. And if you go through the negative group devices, in semi-converter, the negative group devices are uncontrollable devices. Irrespective of the firing angle, the conduction period of these devices must be constant. So from 0 to 120, D2, 120 to 240, D3, after that D1 and D2. From this, you draw the table from 0 to 30. T2, D2 comes to the on state. T2, D2 means those lies on same leg, like here. T2, D2. See, here T2, D2 must lies on the same leg. If these two devices are in the on state, what happens? This simply acts as a short circuit across the load, then the output voltage is 0. So, from 0 to 30, output voltage is 0. 30 to 120, T3, D2 are in the on state. If 3, 2 are in the on state, 3, 2, VCB, first device represents the positive group and the second device represents the negative group phase. So, T3 phase C positive, D2 phase B negative, hence why VCB appears as the load. 120 to 150, T3, D3, again those devices are on the same leg, output voltage 0. 150 to 240, T1, D3, V0 is equals to VAC. 240 to 270, T1, D1, V0 is equal to 0. 270 to 360, T2, D1, then V0 is equals to VBA. Then, if you go with the waveform, from alpha 0 to 30, output voltage 0. 30 to 120, VCB appears as the load. 120 to 150, 0. Again you have some voltage, 0. Again you have some voltage. If you go through the continuous conduction mode, then this is the current waveform representation. From 30 to 120, positive output voltage. What does that means? VCB is available across the load due to the conduction of T3, D2. Then what is the current flow through the circuit? T3, D2 now. Then phase C, T3, R, L, D2, B and C. This is the current flow through the circuit. During that condition, there was some energy must be stored in the inductor. There was some energy must be stored in the inductor. So, the current flow through the load is rising in nature, and from this 120 to 150, T3, D3 come into the picture. So, due to this T3, D3, what happens here? Due to the conduction of T3, D3, the energy stored in the inductor is discharges to the load through T3, D3. Hence, output voltage is 0, but the energy stored in the inductor is discharges to the load through T3, D3. Hence why, see here, the discharging current will be flows like this, and T3, D3 will be in the on state. Up to the next instant where the VAC is available across the load, up to that the discharging current will be taken place. And again, we have the voltage corresponding that there was some energy must be stored in the inductor. Again, discharges, charges. So, if you observe here, the current never reaches the 0. Hence why it should be operates in continuous conduction mode. It should be operates in continuous conduction mode. If we go through the continuous conduction mode, average output voltage must be same. V0 is equals to 3 VML by 2 pi into 1 plus cos alpha. Output voltage should be same, but the waveforms and the operation should be changed. And if you go through the RL load under discontinuous conduction mode, then we will observe the voltage and current waveforms. Here I just want to draw the output voltage for alpha equal to 120 degrees under discontinuous conduction mode. And we also observe the current waveform. So if you want to draw the output voltage for alpha equal to 120, just you draw the timing diagram first. For alpha equals to 120 degrees na. So if you choose alpha equal to 120, where the T1 comes to on state, 120 plus 60, 180 to 300 T1, 300 to 420 T2, next T3, before this 60 to 180 T3 and here T2. And in the lower group 0 to 120 D2, D3, D1, next D2. So from this 0 to 60, T2, D2, then output voltage is 0. 60 to 120, T3, D2, then V0 is equals to VCB. 3 to na VCB. 120 to 180, T3, D3. Again these devices must lies on the same leg. Again the output voltage is 0. 180 to 240, T1, D3. V0 is equals to VAC. 240 to 300, T1, D1. Output voltage is 0. 300 to 360, T2, D1. Then V0 is equals to VBA. So here we consider discontinuous conduction mode. Discontinuous conduction mode means the energy stores in the inductor is completely discharges while the next incoming SCS comes to the on state. So the effect of that extinction angle is considered 30 degrees. That means you go through the VCB 60 to 120. Output voltage is VCB. Just you go through the here. First you note down those time intervals. 60, 120. Here it is 180. It is 240. 300. 360. From 60 to 120, you have the output voltage is VCB. Just you follow the VCB line. Where is the VCB line here? This one, VCB. Here, 60 to 120. This pulse is available across the load. Right. During that condition, the current flow through the circuit is rising in nature. the current flow through the circuit is rising in nature. If this current is discharges up to this 180, we are getting continuous conduction mode. If you go through the discontinuous conduction mode, the energy stores in the inductor is completely discharges at 150. That means that extinction angle is considered up to 30 degrees extra. So here 60 to 120 you are getting VCB na. VCB means which are in the on state? T3 D2, right? T3 D2. So here T3 D2. Next, the energy stores in the inductor is discharges due to the T3 D3. And this 150 to 180 output voltage is 0, and here 150 to 180 the current is also 0. Current is also 0. Why? Because from 60 to 120 there was some energy must be stored in the inductor and some power should be transmitted from source to the load. After 180 the energy stored in the inductor is discharges to the load through T3 D3. At 150 degrees that energy is completely dissipates or discharges and the T3 goes to the off state. So here except D3 all are in the off state. Hence why output voltage 0 and output current is also 0. Again from 180 to 240, 180 to 240, T1 D3. T1 D3 means VAC. Where is the VAC line? Go through that VAC line from 180 to 240. This pulse is available across the load. So 180 to 240. Here we have the output voltage. Again the current flow through the circuit is rising in nature. At 270 that energy is discharges, and here again this T1 D1 will be in the on state. Here it is T1 D3 will be in the on state. So in this manner you are getting the output voltage. And similarly 240 to 300 voltage 0 and current is also 0, and again here (300 to 360) you have the voltage and again 0. Here charging, discharging, discharge. This is the output voltage waveform for RL load discontinuous conduction mode. If you go through the RLE load and continuous conduction mode, you are getting that the operation is similar as that of the RL load. If you go with the continuous conduction mode and whether it is the RL load or RLE load, then there is no difference. That means in continuous conduction mode there is no effect of the back EMF. If you go through the discontinuous conduction mode, then we are able to observe the effect of back EMF. Like I am going with RLE load under discontinuous conduction mode, the current waveform should be simple like this. Output voltage will be varies. Where the current is 0, where all the devices are in the off state, then back EMF is coming to the picture. Back EMF is coming to the picture. Then the output voltage becomes here yes, the output voltage where the output current is 0, in that portion the back EMF is coming to the picture here like this, and here also current 0 and here back EMF. Where the current is 0, up to that output voltage is 0, and if the current flow through the circuit is 0, then the back EMF is coming to the picture. So this is the output voltage representation. Here this is the representation of back EMF. This is the output voltage waveform under discontinuous conduction mode if RLE load, if you go through the RLE load. Under continuous conduction mode, there is no effect of the back EMF. If you go through the discontinuous conduction mode, especially where the output current is 0, in that portion the back EMF acts as the output voltage. So this is a simple representation of three-phase semi-converter or off-control converter with R, RL and RLE loads. If you go with RL and RLE loads, continuous conduction mode and the discontinuous conduction mode. So coming to this effect of source inductance on single phase full wave converter. So we have the circuit diagram of this single phase full wave converter or fully controlled converter is like this. And here you have the source. T1, T2, T3, T4 and here you have the load. If you go through the RL load, then this is the circuit diagram representation. Here Vs is equals to Vm sin omega t. So effect of source inductance means if you have the three single phase full wave converter like this, then what is the average DC output voltage here we are getting under continuous conduction mode? V0 is equals to two Vm by pi cos alpha. V0 is equals to 2 Vm by pi cos alpha. Here we are able to collect this much amount of the voltage whenever the source does not have any internal impedance. If the source internal impedance is 0, then you are getting the output voltage like V0 is equals to 2 Vm by pi cos alpha. But coming to the practically, the source possesses some internal impedance. The source have some internal impedance. Due to that, we are not able to collect this much amount of the voltage, which is V0 is equals to 2 Vm by pi cos alpha. Then what is the effect of the source impedance? For example, if the source impedance is considered as the resistance, that means if the source has some internal resistance, then depends upon the load, there was some current flow through the internal impedance. If you made to pass some current flow through that resistance, what happens? There was some voltage drop will be available across that resistance. The remaining voltage is available across the load. Then V0 is equals to, what happens here? V0 is equals to 2 Vm by pi cos alpha minus I0 into Rs. If you consider the internal impedance as a purely resistance, then the output voltage becomes 2 Vm by pi cos alpha minus I0 into Rs. Here I0 into Rs is the voltage drop across the source impedance and 2 Vm by pi cos alpha, here 2 Vm by pi cos alpha minus I0 into Rs is the available average voltage across the load. If you have inductance as the source impedance, then what happens in the circuit? If you have the purely resistive as the internal impedance, then that is the output voltage waveform. V0 is a voltage expression. V0 is equals to 2 Vm by pi cos alpha minus I0 into Rs. If you have source inductance, then Here V a source, Vs equal to Vm sin omega t. Here you have the source inductance, and this is the T1, T2, T3, T4. Here we have I0 and R and the L. Here the output voltage across the load. So due to the presence of the source inductance, the equivalent circuit will becomes here it is V1, assume this is V2, here we have the source inductance, and here it is T1, T2, and here it is T3, T4, here have L, R, and this is the I0, and here this is the V0. This is the equivalent circuit. If you have the source inductance, then what happens? Then what is the effect of the source inductance on the performance of the single phase full wave converter will be discussed. So here we go with the voltage and current waveforms. Here it is the V1 and it is the V2. This is the Vm. Considered as gate pulses. Here I just want to draw the output voltage and consider the current. These are the gate pulses for first and the second thyristor. These are the gate pulses for third and fourth thyristor. And here we have again 1 and 2. And here we have 3 and 4. And it is alpha, pi plus alpha, 2 pi plus alpha, 3 pi plus alpha. And for sake of simplicity, to understand this effect of source inductance on the performance of single phase full wave converter, assume you go through the continuous conduction mode and constant load current. So during the positive half cycle of the supply, what happens in the circuit? T1, T2 are in forward bias, T3, T4 are in reverse bias. At omega t is equal to alpha, we provide the gate pulse. At omega t is equal to alpha, we provide the gate pulse to the first and second thyristor. Then T1, T2 comes to the on state. Before 0 to alpha, what are the conducting SCRs? Before 0 to alpha, here T3, T4 are in the on state. If T3, T4 are in the on state, then consider the load current is I2, and T1, T2 are in the on state, consider the load current is I1. So here from 0 to alpha, T3, T4 are in the on state, then output current is I2. So you draw the output waveform like this one. This is the output current which is having continuous and constant. So this is I2 which is equals to I0, right. At alpha, T3, T4 are the outgoing SCRs, T1, T2 are the incoming SCRs. So if there is no source inductance, then immediately the output current is transfers from outgoing SCRs to the incoming SCRs, and from alpha to pi plus alpha, T1, T2 are in the on state and T3, T4 are in the off state. Again you have continuous current, but due to the presence of this source inductance, it does not allows the sudden change of current flow through the circuit. One of the important property of the inductor, it does not allows the sudden change of current. Due to that, what happens here? Due to the presence of the source inductance, the output current is slowly transmits to the T1, T2 and T3, T4 are slowly goes to the off state. That means here actually I2 is equals to I0. If you provide the gate pulse to the T1, T2, then what is the I0? I1. So here it is the I1 which is having the magnitude I0, but in this case, in this portion, what happens here? The current flow through the T3, T4 and you have some current flow through the T1, T2. During this portion, in this cross period, all are in the on state. T1, T2, T3, T4 are in the on state. So if T1, T2, T3, T4 are in the on state, what happens? This is a simple circuit flow through the current flow through the load. If you have T1, T2, T3, T4 all are in the on state, then T1 is in the on, like this. T1, T4 are in the on state, T2, T4 are in the on state. Then if all these devices are in the on state, the output voltage is 0. So here output voltage expression is, or output voltage waveform is from alpha to, here this one is considered as the mu. The mu is defined as overlap angle. The overlap angle is exists whenever the source has some internal inductance. Due to the presence of the internal inductance, the output current does not immediately transfers from the outgoing SCRs to the incoming SCRs. Due to that, as long as the overlap angle is present, all these devices are in the on state. Due to that, the output voltage is 0. So here the output voltage is 0. And at alpha plus mu, T1, T2 comes to the on state. Then output voltage simply follows from this alpha plus mu to pi plus alpha. So this portion is available across the load like this. And again the current is continuous up to pi plus alpha. Up to pi plus alpha. Again at pi plus alpha, we provide the gate pulse to the T3, T4. Here this is the current flow through the load due to the conduction of T1, T2. At pi plus alpha, T1, T2 are the outgoing SCRs and T3, T4 are the incoming SCRs. So the output current does not immediately transfers due to the presence of the source inductance, hence why it will take some time. So in this portion, again all the devices are in the on state, again output voltage is 0. And here onwards you have I2. So from this pi plus alpha plus mu to again 2 pi plus alpha. You have the output voltage. And the current waveform is simply like this. And again here at 2 pi plus alpha, again we provide the gate pulse to T1, T2. So here T3, T4 are the outgoing SCRs and T1, T2 are the incoming SCRs. Again this, there is a overlapping period and again like this. Like this. So output voltage waveform will be, it is 0 and 0 like this. So here if you go through this one, here T1, T2. In this portion where the output voltage 0, T1, T2, T3, T4 are in the on state. And here also T3, T4. And here also T3, T4. Here T1, T2. This is the output voltage and output current. If there is no source inductance, then immediately the output current from T3, T4 is immediately transfers to the T1, T2. Then you are getting the continuous current waveform like this. And you have the negative pulses, continuous negative pulses are available. But due to the presence of the source inductance, where the overlapping period exists, overlapping period means the portion at which all the devices are in the on state. Due to the presence of the source inductance, it may cause, if you provide the gate pulse to the incoming SCRs, then the outgoing SCRs and the incoming SCRs together in the on state. At omega t is equal to alpha, we provide the gate pulse to the T1, T2. Before alpha, T3, T4 are in the on state. Then the output current is due to I2, no problem. At alpha, we provide the gating to the T1, T2 na. Hence, from alpha to mu, that mu should depends upon the value of inductance, source inductance. If inductance is low, then this overlapping angle is also low. Within the short period of time, the current is transmits from outgoing SCRs to the incoming SCRs. If source inductance is high, then this overlap angle is also high. So that overlapping period is simply defined as, due to the presence of the source inductance, the 4 SCRs together are in the on state. The duration is simply represented by the overlapping angle. So in that overlap angle, the output voltage is 0. So what you observe here, if you have the source inductance, there was some reduction in the output voltage. If there is no source inductance, from alpha to pi plus alpha, or from, see here, from pi to pi plus alpha, we have the continuous negative pulse. But due to the presence of the source inductance, from pi plus mu to pi plus alpha, in this portion, the output voltage is 0. From pi plus alpha to pi plus alpha plus mu, the output voltage is 0. So how much voltage will be dropped due to the presence of the source inductance? Will be find out now. So in the overlapping period, if all the thyristors are in the on state, then you apply the KVL for this loop. What you are getting here, by applying KVL, minus V1 plus Ls into di naught by dt is equals to or V1 to write the voltage expression across these 1 and 2 and 3 and 4. What you are getting here, V1 minus Ls into di naught by dt is equals to V2 minus Ls into di naught by dt. So by simplifying this, what you are getting? V1 minus V2 is equals to so here V1 is equals to Vm sin omega t and V2 is equals to minus 2Vm sin omega t. So substitute these values here. 2Vm sin omega t is equals to 2Ls di naught by dt. 2 gets cancelled, and finally here di naught by dt is equals to Vm by Ls into sin omega t. And here di naught is equals to Vm by Ls sin omega t into dt. And here by during that limitations, so if you go through this current waveform at omega t is equals to alpha, what is the I1? That is equals to 0. And at omega t is equals to alpha plus mu, what is the I naught? It is I1. At omega t is equal to alpha, I naught is equals to 0, and at omega t is equal to alpha plus mu, I naught is equals to I1. From this, see here, this is the I1 expression, I1 waveform. So at omega t is equal to alpha, this I1 is 0. At omega t is equal to alpha plus mu, I1 is equals to I naught. So you write the limitations like integral 0 to I1 di naught is equals to Vm by Ls integral alpha by omega to alpha plus mu by omega. From this, at omega t is equal to alpha, then t is equals to alpha by omega. Then we write the limitations like alpha by omega to alpha plus mu by omega sin omega t d omega t. So by simplifying this, what you are getting here? I naught is equals to Vm by Ls minus cos omega t by omega between the limits alpha by omega to alpha plus mu by omega. So I naught is equals to Vm by omega Ls cos alpha minus cos alpha plus mu. From this, cos alpha plus mu is equals to What you are getting? Cos alpha plus mu from this expression. Vm into cos alpha minus I naught omega ls by Vm. Vm into cos alpha by omega ls minus I naught. Then cos alpha plus mu. Cos alpha plus mu is equals to what you are getting here? Vm into cos alpha minus I naught omega ls by Vm. If you go through this output voltage waveform, what is the average DC output voltage here? From alpha plus mu to pi plus alpha, we are getting the output voltage. Then the average DC output voltage is given by V naught is equals to, for completion of one full cycle of the source voltage, we are getting the two pulses. So 2 by 2 pi integral alpha plus mu to pi plus alpha sin omega t d omega t. So by simplifying this expression, 2 gets cancelled. Take Vm outside, Vm by pi. Integral sin omega t is minus cos omega t between the limits alpha plus mu to pi plus alpha. So what you will write here? Vm by pi into minus cos pi plus alpha plus cos alpha plus mu. So by simplifying this, Vm by pi minus cos 180 plus theta is minus cos theta minus of minus plus cos alpha plus cos alpha plus mu. So V naught is equals to Vm by pi cos alpha plus, what is the cos alpha plus mu here? Here what you are getting here? Vm into cos alpha minus Vm into cos alpha plus mu, that is equals to I naught into omega ls. And here or I naught omega ls by Vm, no problem. Then cos alpha plus mu is equals to cos alpha minus Vm divided by I naught into omega ls. Then substitute that value here. Cos alpha plus mu is equals to cos alpha minus Vm by I naught omega ls. So what you are getting here by simplifying this expression? I naught omega ls by Vm. Then substitute that value here. Omega ls I naught by Vm. So by simplifying this expression, what you are getting? V naught is equals to cos alpha plus cos alpha 2 Vm by pi cos alpha minus Vm gets cancelled, omega ls I naught divided by pi. So finally V naught is equals to 2 Vm by pi, here you have cos alpha, 2 Vm by pi cos alpha minus omega is written as 2 pi of ls I naught divided by pi. Pi gets cancelled, and final output voltage is 2 Vm by pi cos alpha minus 2 f ls I naught. Then from this output voltage expression, if you have the source inductance, then this 2f ls I naught, that much amount of the voltage will be dropped across the inductor, and the resultant voltage across the load is given by 2 Vm by pi cos alpha minus 2f ls I naught. If there is no source inductance, then what is the average DC output voltage across the load? 2 Vm by pi cos alpha. If we have the source inductance, here F is the frequency, L is the source inductance, I naught is the load current, all are known values. That much amount of the voltage will be dropped across the inductor. If we have the resistance also, then what is the average DC output voltage? This 2 Vm by pi cos alpha, that voltage must overcome this 2 f ls I naught minus I naught into Rs. That is the final average DC output voltage if you have the source impedance is the combination of resistor and the inductor. Then the average output voltage is given by 2 Vm by pi cos alpha minus 2 f ls I naught minus I naught into Rs. This is the average DC output voltage by considering the effect of source inductance. So from this topic, what you observe here, the effect of source inductance on single phase full wave converter means due to the presence of the source inductance, the resultant voltage will be reduced by an amount of 2f ls into I naught. 2f ls into I naught. Here this 2 simply represents number of pulses in the output voltage waveform. Similarly, if you go through the 3-phase full wave converter, what is the average DC output voltage across the load? 3 VML by pi cos alpha. That much amount of the voltage will be collected across the load if the source does not have any internal impedance. If the source have internal resistance, then if you go through the 3-phase full wave converter, at a time two SCRs will be in the on state, one from the positive group, another from the negative group. That means two phases must be in contact with the load, corresponding that you are getting the line voltage. So if the per phase resistance is taken as Rs, then minus 2 I naught Rs. This is the voltage drop across the source resistance. And by considering the inductance, then minus 6 F Ls I naught. This is the final DC output average voltage across the load for 3-phase full wave converter by considering the source impedance. If there is no source impedance, then output voltage is 3 VML by pi cos alpha. If you consider the source impedance as the combination of resistor and the inductor, then minus 2 I naught Rs is the voltage drop across the resistor and 6 F Ls I naught is the voltage drop across the inductor. So the final average DC output voltage is given by 3 VML by pi cos alpha minus 2 I naught into Rs minus 6 F Ls into I naught. Where we consider the 6 here, if you go through the 3-phase full wave converter, it is a 6-pulse converter. For completion of one full wave in the source, we are getting the 6 pulses in the output voltage. Hence why we will write here 6 F Ls into I naught. Whereas if you go through the full wave converter, for completion of one full cycle, we have the 2 pulses in the output voltage. Hence why we will write 2 F Ls I naught. This is the last topic of the second unit, effect of source inductance on the performance of full wave converters, either single phase full wave converter or 3-phase full wave converter. So at this end of this lecture, student will be able to explain the operation of single phase half wave control converter with RLE load and explain the operation of single phase and 3-phase full wave converters and effect of the source inductors. Okay, thank you.